Today, he'll be introducing us to deep soil measurements in CABBI with his presentation, Unlocking the Mysteries of Deep Soils and Bioenergy Systems. So I'll turn it over to you now.
All right, thanks, Leslie. Thank you for the great introduction. So today I'm going to talk about work we've been doing looking at how bioenergy crops impact deep soil carbon and carbon cycling and microbial processes. All right, so first thing I want to do is the first thing with deep soils is that it starts with hard work from a lot of folks. I just want to thank all the people in the lab over the years who've helped out with this, including Dominic Cifelli, Jess Burke, Joanna Ridgway, Zoe Pagliaro, and also Noah Wallace, who also helped with this as well. And so we took a lot of pits. They dealt with some adverse weather conditions the first year. The first year we also didn't have a bulldozer. And so a lot of this really wouldn't be possible without the elbow grease of all these folks. And I actually did some work too. And I'd also like to thank some of the folks at CABBI that have also really helped and been instrumental with this research. All right, and so why deep soils? So as a soil scientist and as an ecosystem ecologist, you know, a lot of us are all really guilty of focusing on the top 15 to 30 centimeters of soil. Most of this is because it's easy. You can go out, take a soil core, take a quick sample, you know, you're in and out of a plot in 5-10 minutes. But this neglects the fact that deeper soils contain nearly half of all soil carbon. And so you're looking at here at an old figure from Javagi and Jackson back in 2000. You're looking at grasslands, shrubs, and forests. And you can see that as you get below 40 centimeters, there's a whole lot of carbon and that's sitting down at those depths. And it can be anywhere, you know, around half of all the soil carbon in the world. And, you know, we didn't, in our research, we haven't gotten down to the 100 to 200, you know, the 1 to 2 meters or 2 to 3 meters, but there's also carbon down there as well. And the other reason why this deep soil carbon is really important is that it also sticks around longer. And so this is a graph from a paper showing you how old the carbon is as you go down in depth. And the one thing you can notice is that as you get over here in this, you know, 100 centimeter range, you're seeing that a lot of the carbon is this much older carbon. And so what it suggests is that if you can get carbon down there, it's going to stay around for a long time. And one of the things we can assume is that deep soils are going to act the way as shallow soils. And so when we think about soils, you know, as we go from the top 15 centimeters down to a meter, there are likely strong gradients in inputs, you know, so in the topsoil, you're getting harvest residues, and also most of the root biomass is in that top 30 centimeters. Because there's more inputs and more carbon available in those top layers, you're also going to have greater microbial biomass and activity in the shallow soils than in the deeper soil layers. There also could be gradients in mineral surfaces. And so in the top layers, you might not have as much mineral surfaces that can stabilize soil carbon as you would in the deeper soils. And then also there can be biophysical properties, including, you know, oxygen concentrations, temperature, and moisture that can all impact microbial activity and how much carbon sticks around in these deep versus shallow soils. And so one of the things we've been really interested in is how do these gradients and all these different factors impact the pool size information of soil organic matter across, you know, going from the top 15 centimeters down to a meter in depth. And one thing I want to do is just, because this is really integral for a lot of the, you know, what I'm going to be talking about, is that not all soil carbon is the same. And so when we think about soil carbon, we kind of think about it in two broadly distinct pools. The first is this particulate organic matter pool, which you can think of as undecomposed or minimally decomposed fresh litter inputs. It's not very stable. It can be unprotected. And so if the microbes can get over their energetic constraints, if it's warmer, they have plenty of soil moisture, they can break that down. Sometimes it can also be protected in aggregates. Its residence time is years. But one good thing is that if you can kind of build this particulate organic carbon indefinitely, it's not going to saturate. You're not relying on anything else to keep it there. The other carbon pool we're really interested in is this minerally associated organic carbon. And this is coming from highly decomposed microbial products. It can also be due to the direct absorption of DOC in soils. And what happens is this goo or this DOC can stick to mineral surfaces, and it can be protected from microbial attack. And so the residence time of this can be decades to centuries, But the one thing is that it can become saturated. So you can run out of mineral surfaces that this stuff can stick to. And so presumably you can think about, when you get thinking about shallow versus deep soils, you may also think they may differ in the form of carbon that's there and also the ability to form new carbon. And so when we think about shallow soils here, we're looking at, we have higher carbon inputs. So we have a lot of carbon that can be particulate organic carbon. It can stick around longer. Those dead roots might not be decomposed, sticking around. We also have higher rates of microbial decomposition. And then also, you can think of it this, because we have so much inputs and we have such high microbial activity in those shallow soils, most of those mineral surfaces are more than likely saturated, or you're not going to be able to stick a lot of new mineral-associated organic carbon in there. By contrast, in deep soils, we have lower carbon inputs. So we're not getting, you have some roots, you maybe have some DOC leaching, but you're not going to be driving those microbial products that can kind of stick and make mineral-associated organic carbon. We have lower microbial decomposition. But the flip side is we have more available mineral surfaces. So we might be able to stick more carbon. If we can get the carbon down there, it might stay around longer because there's mineral surfaces for it to sort to, and there's not a lot of microbes that are going to eat it. And so when we're thinking about our research in this, we're thinking about, what's, our problem is that our current crops reduce soil carbon. And one of our CABBI solutions is this idea that cultivating deep-rooted perennial crops may enhance soil carbon storage. But what our key unknowns are is, what factors influence these depth gradients and carbon stocks. And also, we're really interested in if deep soils differ from shallow soils and their potential to stabilize new carbon inputs. So if we can get carbon down there, does it stick around longer in deep soils than shallow soils? And so a lot of this is the results of people power in the field. So in 2022, we started our odyssey into deep soil research by going out to Soy Face. And there they had over a 20-year-old miscanthus stand. And in 2022, we did not have a bulldozer. So we were digging these things by hand with shovels. I wasn't there the first week when it was 90 some odd degrees, but I came the second week when it was 70 and it was still brutal. And so what we did is we excavated kind of a larger pit, kind of an access area. And then we went down and we did a meter by meter face into the miscanthus plot. And then we excavated 30 centimeters into the plot. And we took all that soil out. And so we took all that soil out. You could kind of almost take it out like you're chopping up a cake. You're cutting out these little layers and they would come out in these blocks. And then we sieved it all in the field to get all the roots and rocks and everything else out. We saved all the roots. We sieved everything. We weighed all the soil so we could calculate bulk density and other things. And then we had these soil samples that we would, the sad part is we sieved all the soil and then we would just fill up like a 1 gallon Ziploc bag for a homogenized sample that we brought back. And then we'd have to throw all the stuff we sieved back in. And honestly, the hardest part of this research is not digging the hole, it was the sieving. This really took a lot of time to do, and it was very, very time consuming. And so, I'm just going to show a little bit of data from this project. And so one of the things we found in our 2020 miscanthus pits at Soy Face is that we saw these strong depth gradients of carbon stocks and fractions. And then we were able to kind of think about what was driving them. And so here in A, you're looking at total carbon concentration, so grams carbon per centimeter cubed going down with soil depth. And you can see that the top soils had much greater carbon concentrations than the deeper soils. They also had more MAOC and also more POC. But one thing I'm not showing you here is that when we look at that gradient in the MAOC to POC, we actually find that deep soils have a greater contribution of mineral-associated organic carbon to their total soil carbon than do the shallower soils. And one thing we did is we took all this data, we measured a bunch of other things, but I don't want to show a ton of data here. We measured things like fine root biomass, different enzyme activities, nitrogen mineralization. We also took soils out of from the lab, and we just incubated them in jars to get microbial respiration. And so we took all that data and we threw it in a linear mixed effects model. And we looked at what were the best predictors of soil carbon, total soil carbon, mineral associated organic carbon, and particular organic carbon. we found two things that made sense. One was, well, it was inputs, so it was fine root biomass. The other thing that we found that made sense, it was outputs, it was microbial respiration. But we also found that this N-acetylglucosaminidase activity was also a strong predictor of our soil carbon gradients. And what this enzyme actually does is it breaks down microbial cell walls. So it might be indicative of microbial recycling of necromass or microbial production of cell walls. So we had basically it's indicative of the spinning that microbial wheel where you're getting more microbial biomass production, which could lead to more mineral associated organic carbon. And one thing I forgot to mention is when we looked at this for particulate organic carbon, it was just inputs. So if you could get it there, you would have more particulate organic carbon. The other thing we did with these soils is we also did a quick experiment in the lab where we added 13C labeled glucose to these soils just to see how it would impact whether it would form mineral associated organic carbon or whether it would be blown off. And one thing we found is that we didn't see any differences across the different soil depths in how much of that 13C was stabilized in the soil. But when we just looked at the change in mineral associated organic carbon over the course of the incubation, we found that in the shallow soils, when we added when we added that simple carbon input, we actually led to soil carbon losses here in the top areas. But when we added it to the deeper soils, it even led to gains or really no change. And so it suggests that, in these shallow soils, we might have carbon that is more susceptible to priming than in these deep soils. So in the end, this is some of the data that you can generate by doing this deep soil research. And the one really cool thing, wrong button, is that this data has really proven valuable for modeling. And so Melanie Hartman and Bill Parton are using this data right now to get basement to model down to 1 meter. And the reason for this is that we had all these combined data sets. We had we had the soil carbon, we had the soil carbon fractions, we had really great root biomass data, we had all the microbial data, and it just gave them this great test site to parameterize and develop the model. And so that's been a really good key of this deep soil research. This isn't the only efforts that we've done. In 2023, we also went out and dug pits in miscanthus, sorghum, and corn at the energy farm. As you can see, this was a little easier last year, because we had help. We had a bulldozer with a backhoe. And so they dug a nice access pit for us where we just had to go in and excavate what we were working on. Here's Zoe hanging out. Joanna and Jess just sieving. We did a lot of sieving. But the other cool thing, and this is just showing you what one of those faces looked like after we excavated it out. But the other interesting thing we did is we also put in ingrowth cores. And you see that we put them in going horizontally. And in these ingrowth cores, this is a picture of me. You can kind of see the core here, and they're tied together with weed whacker cords. So hopefully if we find one, we can find the rest of them. And what these cores are filled with is they're filled with actually forest soil relies on C3 photosynthesis. And we're putting them in these bioenergy feedstocks that rely on C4 photosynthesis. And so what we can do is when the bioenergy crop starts putting carbon in there, we can actually see the net amount of new carbon it'll put in there over the growing season. And so we've harvested the shallow ones after only a year, but we're going to go back this fall and get the ones out of the deeper depths. And this is going to give us some really good data on root production, but also how much carbon or root carbon that these feedstocks are putting into the soil, how much of it is sticking around, then also how does it vary by depth. All right, and so I think I even went over, so I wanted to leave you with this terrible pun, so I hope you have a deep appreciation of deep soil research. And with that, I'll take any questions. And this is one of the pictures we took the first year, and got a lot of press out of this. This even was on the DOE website, and it's a homage to the movie Holes. So with that, I'll take any questions.
Is the carbon profile in a miscanthus plot for 20 years really markedly different from what you'd see in a cultivated corn soybean field?
Yeah, so we're just actually getting the data back from 2023, and when we look at it right now, surprisingly, we're not seeing any differences between corn, miscanthus, and sorghum in total carbon or how it varies across steps. We haven't looked at the distribution. That's just in total soil carbon, so we haven't looked at the distribution of that stable mineral associated organic carbon versus the less stable particulate organic carbon. But in terms of total carbon, it's not really showing it. And this is corroborating some of the data that's coming out of Evan's lab and also what Jennifer Petridge has done with radiocarbon dating.
Is it because that deeper carbon is like old and it's just been there forever? Is that a reasonable
So
explanation?
the interesting thing is that we do see roots at those depths. So particularly for the miscanthus, we saw there was a fair amount of roots in that deeper layer. I think one of the reasons we don't see the big differences, and this is something that Carl brought up during one of the sustainability meetings, but it's just like we're trying to find, an increase in carbon that's really hard to resolve in soils because they're heterogeneous.
Gotcha. Okay, thanks.
Yep.
Just have a simple methodological question. I didn't understand. You said that you sampled the more shallow horizontally bored tubes this year, and you're going to do the deeper ones next year.
Yep.
Is that from a single site?
So that's all so that's in four. So we put them in each of the blocks for the four replicate blocks for miscanthus, sorghum, and corn. And so we sampled the top ones earlier because we were worried about the harvest and also the tillage maybe disturbing them. And we left in the deeper ones because we wanted to give it more time to see if we could actually resolve anything.
But I guess what I don't understand is how you don't destroy the experiment by harvesting the shallow ones. Doesn't that destroy the ability of the deeper ones to gain any more carbon?
Because they're only, they're 15 centimeters and they're going in like this. And so we basically took out the top ones, and it was during in October, so that nothing was growing. And then they replaced everything, and then the stuff will cultivate and come in later. So we tried to minimize the disturbance, but it was a trade-off between having a measurement at that depth and dealing with the potential impacts of the machinery coming in, the tillage, and everything else.
Got it. Thank you.
Yep.
Edward, do you, since the miscanthus being a perennial there, and then those cornfield, are there other rotation system that's followed on them?
Yeah, they're corn, soy, the corn.
Corn,
Yes.
corn,
Soy. Yes.
soy. And so with sorrel as with the other crops, how do you take that in consideration as comparing a solid perennial with a rotational field?
I think that's something, we're interested in doing in CABBI in general, because corn, soy is kind of the background of what we're working with in the Midwest, and we want to think about planting, perennial grasses as to fuel bioenergy economy in this area. And so I think that's corn, soy is kind of our straw man that we compare a lot of things to.
I'm just curious about the validity of that assumption. I know that Evan used to say that, and I always used to argue with him that it's, what's dominant around here is annual corn soybean rotation, not corn soy. And if you look across the United States, the amount of acres that are planted in maize are the same as the amount of acres planted in soybean, and it doesn't change very much year to year.
Yeah.
Is that real?
So I will say that that's a little bit outside my pay grade. So I'm not the one who set up the experimental site or decided on that rotation, but I'll let others delve into that question more deeply.